So the financial industry, of course, is known as being people who use nanoseconds to steal your money. Working in the financial industry is challenging, but I'm here to talk today about the good guys. There are some, not enough, and I'll talk about that. Now, I will apologize because the part of, at least half the talk, I'm talking about stuff that I was building using the technology. I now happen to be the chief scientist for the company that supplies the technology, so I've tried to remove all the product names and everything else about it. So I'm just talking about the problem. I'm not trying to pitch you any particular technology because it's just too weird and strange and useless for any of you to really want to be bothered using it at all. So, just briefly, I'm just going to go through, first of all, what the problem is. I'll talk about data. Fortunately, we had some great talks yesterday that talked about the euphemism of data science. Basically, we're 85% of the work is trying to get data in some form that you can use it. 5% is data science, and 10% is trying to explain it to people that don't understand basic statistics what it means. I'm sorry, that's the reality, and be prepared if you're in data science. You may find out that you're a data cleaner for a lot of the time. Then I'll talk about a couple of case studies, particularly applicable to financial markets, although cyber analytics has a broader applicability, and it actually sort of complements the talk by Phil, threat metrics. It's something sort of that is a different part of the cyber puzzle. So the basic reason for oversight are to protect companies and individuals from a number of things: financial fraud, identity theft, or intellectual property theft, or actual destruction of intellectual property. We all know that these things are problems of enormous magnitude. And it's also to ensure that companies, individuals, at least in financial markets, try and play by a fair set of rules. And I'm not going to get into whether or not, low latency, high frequency trading should be banned or not. We do have customers that actually execute their code inside the switch, and who rely on the fact that it's actually faster to use satellites, to actually use microwave links and radios, than it is to run fiber. That's a very strange business, and it's an arms race. Fortunately, they're going to get to the speed of light soon, and at that point they too will be limited in what they do, and probably they'll have to think about smarter strategies than just arbitrage in nanoseconds or microseconds. Also, one of the big problems is there are lots of large companies who end up with rogue traders inside them. So one of the other challenges, of course, is applying this sort of control inside the company. The typical sort of things that people look at are algo testing services. Like many areas in software, people doing derivatives and very fast trading have discovered recently that testing is actually a good idea, because there's several financial companies that have just gone out of business, because virtually like Knight Capital and so on, because they had bugs that basically cost them, literally billions of dollars. Market trading surveillance, both internally and across markets, such as ASIC in Australia. We built the market trading system for the surveillance system for ASIC that surveys the Australian market. Corporate trading, then financial forensics and cyber analytics, basically both on the preventative side and also being able to go back and find out what's up. So on the preventative side, basically, it's pretty straightforward. You have to detect and warn, and you do this in various ways. And you basically, on the sort of actual development side, you're trying to ensure that your algorithms work, You do that through testing networks, complete copies of the exchange. For instance, we have everything that's in the Indian exchange, and basically before you can deploy a new algorithm in India, you actually have to run it and test it. You don't have to do that in the rest of the world. So some places actually are ahead in terms of concern for quality in financial markets. Similarly for SLA enforcement and monitoring. On the other hand, those things essentially set off alarms, cause things to happen, but unfortunately we still have the problem that there are lots of very clever people who figure out how to perpetrate some sort of financial crime or financial fraud, and often you may get an alert that something funny has happened, but it may take you weeks, months, or in the case if you're actually going to take it to court, years to actually build a case with sufficient evidence, which is all primarily data-based, to actually prove that this crime has been committed and prosecute the individuals and so on. So this has to look at the history of it. Pretty much you end up looking at the history of many years of data. Basically the stock market is called tick data, and basically that's every single thing that goes on the ticker tape in the old days. So it's a few terabytes a day, nothing huge, but over time it's not unusual to do it. The largest companies, our largest client has 21 terabytes of active data. It's all in RAM, by the way. So they're doing the analysis over that, and you can get pretty challenging. So until recently, regulation, the idea of sort of regulation and automation were just worlds apart. And there's some exciting work going on here at Data 61 in the regulatory area in Canberra, and I don't know whether Linda's here or not, but the looking at regulation, and we're hoping to see maybe that some of that could be applied in the financial markets as well, trying to because it's very hard to turn regulation into code. So one of the challenges is trying to do that. The other problem is the volumes. Until recently, there was no way to process them. The amount of data that goes through the market, particularly when you want to look for very small things, like people playing games with arbitrage and so on, you really have to have very fine-grained tools for looking at it. The recent regulations have made it such that you really can't do this by having people sort of sit at screens and just watch stuff go by, or troll through logs with poor query tools. So pretty much now this year, there's regulations passed in Europe really require that you actually have sufficient compute power to do this, so it's definitely a big data problem. And classically, that if in the cyber world, in the old days, you'd be able to sort of just, okay, well, you can do a signature check, right? I mean, basically, I've got the hash of the, whatever thing's been identified out there and reported to the security authorities, whether or not it's made by one of the virus vendors, we're never really sure, so they can sell more virus packages or not. There have been cases of that. This is like only 30% effective, right? The sophistication today is that you really have to be able to not only look at the window of activity of packets that are coming into your network, you have to be able to look at the history of the packets, because botnets, for example, actually sit buried in regular internet traffic. And so you have to actually observe these things over a long time. So in general, you're in a situation where, as you are in the financial markets in general, where you have to look at the window of real-time data you've seen, often called streaming data. We don't know what streaming really is. It's a definition. It's a window that you can see the data in. It's typically what you can sort of put in RAM or something like that. And all the historical data, which is huge. And you're typically, in the case of a new cyber attack, a zero-day attack, you're probably looking at 4 to 6 months worth of previous data. and it'll usually sit buried inside your network for 3 to 6 months, trying to move horizontally and gain intelligence in your network, figure out where all the patches haven't been applied to the various Microsoft and Oracle products, so it can load up a big boatload when it explodes, try and penetrate as much as it can inside your network. These things are really very sophisticated, and of course, since the Stux virus, basically we begin more and more very sophisticated attacks. So the good news is that we have some tools now in the big data tools, and so I'll just talk about a couple of problems. I'm really pleased that Mark went before me, and a couple other people talked about how great the tools are in big data. The first thing, of course, is that unstructured data has a place outside your data center. Basically, so if you're serious at all, the last thing you want to do is take data that's actually quite small and multiply it by a factor of 10 by squirting it out in JSON without a schema description or text of some form. This is just the dumbest and most expensive thing to do. Parsing textual data is something that's very hard to parallelize. It's a lot of work. It's bug-ridden. No one should ever store things in text for any persistent basis. So, per Mark's rule, I can't remember which slide it was, but basically, we allow no text in the system. Basically, everything gets parsed and stored on the way in as soon as possible. Even the exchanges are moving from text formats to binary formats. So the financial exchanges are moving to FIX is now using SBT, and a number of other exchanges. Chicago high-speed exchange has gone to binary as well. Of course, then people dumping into data lakes. Basically, this is where you get a whole lot of really cheap hardware because you said you wanted a Hadoop cluster and your IT department bought it for you. Good news, you got a Hadoop cluster. Bad news is they got it lowest bid from somebody who's got really crappy drives but bad CPUs with no memory, and you're supposed to. You got it now, the full power. You don't need to use a computer on your desktop because it'd be too fast relative to the Hadoop cluster. I think Mark made that comment yesterday. You can run a lot of things faster on your laptop than you can in your Hadoop cluster. And of course, you can tell it's really bad because they talk about jobs. I'm old enough to know what a job is. That's basically a bunch of punch cards that you put in the computer mailbox and you wait and your job comes back to you. So now you take your desktop computer. Well, you don't get a desktop anymore because you don't need one because you've got a Hadoop cluster that can do all that stuff for you. So they take your spreadsheet away, which was the only tool that could do anything in R, and put it on the server in the Hadoop cluster. So I'm really sorry if you're in this world, but this is a bloody disaster. And basically, or you put it on the cloud and you find out that IOPS on Amazon really suck. And of course, you don't really know because it really seems cheap to you until you get the bill. But Amazon is a wonderful thing for building new products. It's a good way to go bankrupt if you're actually trying to run a business. If you're bringing in enough cash that you can throw it away, like many American companies are, but that's coming to roost soon. There's a lot of people now seeing their operating costs need to be cut. And of course, the good news is it's written in Java. The bad news is written in Java, and Java doesn't understand value types or how to deal with any reasonable amount of memory. Can't garbage collect these things, and it's just a sad story. But the good news is we have lots of Java programmers who will bust their brains trying to do some simple ETL by coding all this stuff. So, I know a friend who, a large data center in a nameless country, that basically thought that she was running a data science operation and found out she was running a programming shop with lots of Javanauts breaking pipelines and trying to do things and so on. This is kind of the standard stuff, and everybody thinks it's really fun and it's cool because they're doing big data, right? But it's the same old. It's kind of like EJB, early days, right? It's just terrible. And then, of course, you do queries. The query performance sucks. You can't do full joins or anything else because it actually tries to use a MapReduce infrastructure, thousands of intermediate files to replace what can be done by high performance joins by people that actually understand how to build data query languages. So the solution for most people who have Hadoop is basically, I put the money in and I'm really embarrassed, so I got this Hadoop cluster and I've got my data swamp and my HDFS, so what I'll do is I'll install Elasticsearch, right? And everybody will think it's coming from Hadoop, right? So there's a lot of people who do amazing tricks by putting Elasticsearch or Solar or maybe Splunk or something like that in front. But of course, you really can't do any kind of serious join queries or anything like that. And they sort of have a hacky way to deal with time, but they're even more limited. And of course, the only challenge with these is I know a large American retail firm, and they actually run blind for 1 to 4 hours, which is not a great idea because all their log traffic is being indexed into Splunk. And you basically are blind while you're doing the indexes. So it's good to be in a real-time operation. It's fed by Kafka and everything like that. And Kafka falls over. Once you get to 40 or 50 terabytes, it'll just flop out. But most people don't really try these things seriously. They believe the marketing hype, right? It's made in California. It must be cool. I mean, when Google gave up on Hadoop was when Google gave up on MapReduce when they published the paper. And theirs was implemented in fast C++. And then you have Hadoop implemented, by the best of California's university graduates, right? And shipped to you, and then reshipped to you, and then reshipped to you. Basically, this is a big, painful, expensive mess. Unfortunately, this was so raw when it came out that we weren't able to use it, which was really a benefit. I'm very glad that we didn't. So, fast data in capital markets has been going on for a long time. One of the first places to use automation was people dealing with stock data because there's money involved. I just want to give you a bit of history here, since it seems to be the trend always to do the new thing in the the 21st century. Nothing's ever been done before. It's always really new and cool, especially if it's from California. The first column store was actually built in the 1960s at MIT. Keyed files, they called VSAM or B trees, were in the 70s. They're now called key value stores, usually slower. APL was a language built for dealing with arrays with data in memory, dominant in the 70s for thinkers to solve problems. Really was the forefront of the spreadsheet, and basically everything from R to MATLAB to any of the pi numerics is really an implementation of the APL concepts in one form or another. APL was the first language to have idioms or patterns. The difference between is that an idiom in a functional programming language is actually just the way you program, as opposed to something you have to do by hacking together a bunch of Java patterns. Right? So MapReduce, scan, compress, all these patterns which are now in vogue were actually around in APL and Lisp, which pretty much was coexisted at the same time. I worked for many years in network databases, which later became object databases, which never went anywhere, but they got reborn as XML databases, and now you have really inefficient graph databases. All of it was still a technology looking for a problem, in my opinion. Graph analytics is very important. I just wouldn't use a graph database to do it. There's now something called the Lambda architecture. The first Lambda architecture that I'm aware of is done by a friend of mine and the inventor of KDB. Arthur Whitney was the official airline guide database, which used essentially a real-time database combined with a historical database called batch in the Lambda parlance. And so in the financial world, we've used what's called an RDB, the real-time database, and an HDB, the historical database, at least since the late 70s, early 80s. And now, fortunately, this is really cool because we can be cool kids now because look, and it became Lambda, and this year there's got Kappa, which is really just a log database. That's what Kafka does. And recently, Gardner and Forrester, not being able to choose the same name, have now talked about there's this brand new data, the hierarchical transactional analytic processing, or the translegal database, all of which are a good old-fashioned RDB plus a HDB. Boy, the world does go round, doesn't it? Streaming, pub, sub, and the term topic didn't come from California. They, too, were all put in use 30 years ago in financial markets. That's the way most stock transaction systems work. No one cites that when they talk about it, of course. Either they don't know or they just want to be the cool kids that invented it. I trust that it's the latter, the former, sorry. There's, in the financial world, we use lots and lots of small processes that only do one thing. And recently we discovered there's a name for that. It's called a microservice architecture. Basically, functional programming for data, the most important thing that functional programming does is not parallel computing, which is what lots of people thought it was going to do. It's really dealing with data, which is a set of transformations. So the function composition is the winning thing for data, and that's why functional programming is such a key part of data going forward. And so functional data languages have been around for some time, and particularly the technology that we're using was really done in the early 90s and in production in the mid-95. And the good news is that we now can actually teach people because they actually know what map and reduce and flat map and so are. So it's getting easier. For years we just had people screaming at us that we're too weird and stupid and did it wrong. So it's good to be old and cool. So the other thing that Mark mentioned, and also Quentin and so on, is that if you have a lot of data and it's in production, you actually do need a data architecture. And you have to design the data architecture around the volumes. When you're working, with trillions and trillions of data, when you're working with terabytes of data, you can't just, throw it around lightly. You have to actually think about it. So you basically design these databases. So in practice, there is a Lambda architecture, but there's a whole lot of Lambda architecture instances. There's databases that'll crack out the daily totals, the hourly totals, the yearly ones. They'll aggregate it in ways, and they'll provision those databases to different users. The quants will get something so they can do analytics. The production people will get some other stuff so they can do it. The billing people. So there's a lot of designing for this. When you start throwing around terabytes of data or petabytes of data, well, you don't throw petabytes of data. You just take it from where it's lying. You really do have to spend a lot of time in data architecture. And all the things that Mark talked about yesterday and others are really, really important. Oh, sorry. So, if you want to have fast and big, today we have big and slow for most people. Then you have to be able to work with both the real-time database and the historical database. And it seems kind of ridiculous to have to use different tools for doing that, so we didn't know that was a problem, so we actually use the same language and technology for doing both of them. That means you can do streaming, you can do all the things you want to do in either one using the same technology. We didn't know it couldn't be done, so. And of course, these are very popular today because they'll actually, if you go to Gardner's latest reports or Forrester, they'll tell you about how to design these things. And they won't use the word Lambda architecture either because that's not a word they invented. They have to run their own new things so they can sound cool too. After all, basically, you don't pay them $1 million for their crappy reports for nothing, right? You pay them for the buzzwords they come up with. If I sound cynical, I'm sorry, but I actually know what it takes to get in the Magic Quadrant at Gardner. It's $1 million because I paid them while I was at IBM to get there. So this is really a bad industry. And, you know, all the people who go to the Gartner conference should be gassed when they go there. The other problem is you have to provision this to multiple customers, so you have to design ticker plants. The streaming is what we call the streaming engine in finance. It's called a ticker plant because it's got all the ticker feeds coming in, and we structure these into multiple ticker plants, and people pub sub to them and run microservices off them. But typically, you have to provision all sorts of customers, and that's where you do the database architecture. The other thing is we leverage structured data, so basically as soon as we see anything that looks like text, we convert it as soon as possible. And we'll actually crack that in special hardware in some cases. In the cyber case, there's in some companies that will use FPGAs and so on to actually crack the text and take the metadata out and so on and organize it and index it before we even come near the data. So in general, everything we're storing is in binary in one way or another. Although it's horrific, it turns out that batch is often better. So if you actually care about throughput, most people execute 1,000 transactions at a time, not one at a time. This has sort of become popular recently, and Martin Thompson, who did Aaron, Martin and Todd will be back out here for YOW this year. In December, basically, have sort of championed the notion that if you actually batch things up, you don't have this whole problem of all the overhead of trying to do things. So we do batching queries, and we execute single-shot processes for queries. Multi-threading is really great as long as you don't want to thrash the cache. You like to thrash your caches and do things. So even the modern NewSQL databases from Stonebreaker, which you may have heard of, actually have discovered this idea. So the whole notion of actually trying to do multi-threaded queries and so on is kind of nonsense in modern hardware. You know, threads are always a bad idea anyway. Now they're just a really bad idea. Multiple processes, the way things are, much easier, much simpler, and very, very fast. We run something called the Stack benchmark, which is which is an honest benchmark. The Stack actually owns the hardware, the software. You can't even get near the building, and they run the benchmarks. And we run much faster using multiple processes than we can with multiple threads. So there's a lot of old wives' tales, plus a lot of really hairy coding for people that try and deal with threads and do P'ing and V'ing on semaphores, right? Basically, you know, bumping the semaphore up or down. And we also have to handle time series and graphs and all those other things. They turn out to be all just vector problems anyway. In the end, text analysis basically is computing distances in a vector space. Graphs are barely walked over vector representations. So once you get everything in vector form, it goes pretty fast, or as fast as your hardware and data can. The other thing that's really important is that basically we live in a world where manpower is expensive and hardware is cheap. These are just some prices. Actually, Jill Tennant and I did these last May, a year ago May, and we just updated them. Basically, you can buy a terabyte of RAM now for $10,000. And you're begging for a terabyte of storage. Hardware is really cheap, especially compared to programmers, right? You can do nothing with $10,000 in a programmer. A terabyte of RAM, I can probably keep most people's critical data in memory. Makes a big difference. If you take a look at the latest Intel hardware, we work very closely with Intel because we use the vector instructions, the cache, and the memory prefix to get performance. You find out that Broadwell's going to sort of order 48 processors. There's a high-speed network between them. It's actually faster to send a message between processes than to store in memory. So message passing across processes is actually faster than doing memory stores. Very different architecture. Encryption and compression is on board to take advantage of these. And I know I gave a talk in Australia a year or two ago about the new memory technology, but you're going to have 10 terabytes on your laptop next year of non-volatile directly addressable memory. It might be 2 years away because Intel's screwing around with the chipsets. But this is non-volatile memory. So it means that Australia Post can take on Netflix because they can ship you in an envelope every month all of the movies that are out there. And any employee can have a USB key with 10 to 20 terabytes on it to stick into your drive and take home a copy of your entire business. These are very different technologies, but imagine what it does for quants. Every quant can have a history of everything that happened in the market for the entire history of the organization. So they can do queries without any impact on the production system, which is currently a problem today. So that's the world that finance lives in. Finance, fortunately, is usually willing to pay money to get more reasonable hardware, and they know it makes a difference. Not that every bank is like this, because there are many banks that are dominated by your classic IT department. And I noticed that Quinton had all of the organization reporting to him, and I saw a number of envious groans in the audience. In the end, most people in the trading side own their own hardware. Some of them build their own hardware. So a lot of people building with FPGAs and custom servers. So basically, for the market data, we go pretty quickly through market surveillance. There's a whole lot of rules. These rules have to be complied with. There's a bunch of international standards. And basically, what happens is a whole lot of analysts and regulatory people have to build a lot of rules. So there's a lot of decision table-like logic, basically to find things like an abusive squeeze. So great names for the kind of things that are illegal manipulations in the market. So there's a lot of these things. So basically, you end up with a system that basically consists of a few basic parts that basically looks for things that are bad in the live data and looking back historically, because often you don't really know it's bad until you see something else, and there's the pattern, same problem in cyber. And basically you have to suck in every disgusting form of data from different markets, and you find out that Indonesia sends you data some days that look like this and other days that look like that, and the New York Stock Exchange is going to change all the format of its data in October on the same time, and this is actually happening this year. They're changing the format of tick data. They're renaming all the fields, changing it all to common to limited CSV, and changing the formats of the actual fields themselves, and they're going to do that while switching their data center in mid-October. And that's what you live with. So it's not quite as dirty as IoT, because sensors lie even more than stock markets, but it's still a pretty messy problem. So you end up with a system where ticker plant streaming, some RDBs, a bunch of these things, and basically you run a whole lot of rules through these data, give it alarms and see things like that. And you end up running both batch and real-time alerts, because you have to look for some things that take time to compute, they run in batch, and for the other things you're running real-time alerts. And there's a whole lot of really exciting black screens like this that I know you want to see closely. But basically they get alerts and monitors, and they have the ability that at some point they see something wrong, they can go back and say, I want to be able to replay these transactions. So market replay is a key thing, also useful for something called back testing, so you can actually see, well, if we ran our algorithm on the market as it was then, what would our algorithm do, or our machine learning. I have a good friend that his family's money is traded with a deep learning network, so he's a really gutsy guy. He's not actually allowed to look at it until 2 weeks after, because he works for another company. So somebody who really believes in testing his software. He said he didn't work when he didn't know what testing was when he worked at Deutsche Bank, but now it's his own family money. He does a lot more testing. So the cyber case is really hackers, insider trading, the kind of thing you normally hear about. And I think something that was brought up is basically, you probably see, human eye is often beats machine learning and lots of other things, because machine learning is good at finding things that generally you already know about. But just looking at data, if you actually look at these graphics, they look really terrible. That's because they're designed by a real professional UI designer who actually figured out that these people have to look at this stuff all the time and don't want to be wowed by it. So they're actually terrible looking by design. But you can see these little patterns here, these little patterns here. These actually happen to be bad guys that all these people are calling to check when or not they should actually do something bad. And you just poof that data on the screen and you see those patterns. Human eye is very fast. Then you can go and say, okay, set the machine learning and go look for this pattern. And then you can get a function, probably with 47 variables, which is way too complicated. Delete 40 of them and run the function and fit it. I think machine learning neat, but it isn't free. It's a tool, and one of the scary things is, do you know what your system's doing if it's trading with machine learning, or worse, controlling systems? So we basically have to do a bunch of things, finding all the patterns in the attack, find the bad actors, look at their reputations. We can get some of that by talking to threat metrics, because they'll tell us about all the devices and who some of the bad guys are. They have a big network of knowing where all the stolen cards are and things like that. So I can send a message to Phil, and Phil can give me that information. He just charges me too much, but I'm sure it'll get better with time. So our problem was basically, we're working with a next generation of cyber analysts. People are basically looking for attacks that haven't happened yet. So this is sort of a classic problem. We worked on this problem in electronic warfare too. Basically, what do all future enemy attacks look like? It's hard to write the story cards for that, right? Write down the requirements. What do all future attacks look like? Well, you can't do that. So the way you do that is by building models of synthesizing what you think future attacks might look like. Essentially, typically behavioral models, and then you have to run those in the live stream. So basically what cyber analysts do in the world we do is they basically build models. They deploy those models live into the network, and the models just sit there processing until one of them goes, hi, I'm model 477. I think that I'm active. At that point, a cyber analyst gets a call. Cyber analyst looks at it and says, oh, damn, another one of my bugs. I shouldn't have been programming in Java. Let me go back and do that in a thinking man's language. Oh, now it's working. Okay. And then they push a button and deploy it to a network control center, typically with a custom graphic so that the network operators can do it. So to build this, we basically had a challenging problem. We needed to find a runtime, we needed to find a data language, and we need to make it usable. Those things are all sort of mutually exclusive, by the way. Basically, if it runs really fast, it's probably hard to program and probably difficult to use. That's just kind of the free lunch, There is none. So basically, it's a simple world. Basically, we develop the algorithms, we deploy them, and then we actually have to deploy them to the field. In our case, we had another requirement. Basically, we have to be able to run these things. One of the things you want to be able to do is do the detection near the edge of your network. So we're working with global organizations. The global organizations, we actually deploy the algorithms out through their network. So they run in the devices in the network. So we have the requirement to be able to distribute the analytics throughout the network. So that's a ARM0. If you've not seen one, that's Apple mouse beside it. That's an ARM core. And it's running the same vector execution engine that runs in the 21 terabyte machine that I was talking about. That's one of the reasons. So basically, we picked this strange, funky technology, which is a vector execution environment at the bottom. So it's a high-performance vector store. There's a wide spectrum functional programming language on top of it, and of course it's sucks and blows whatever C or ODBC or whatever else. All the wonderful standards that are out there, as slow as you can pack and move data both ways. And then we provide a set of end user tools on top of that so that humans can use it, because cyber analysts typically are specialized in different things like geography, crime patterns, and so on. They're not really specialized in how to do programming. So it's actually fun to be able to build an environment for people that aren't programmers, because programmers are such a pain to actually work with. And so we basically built a bunch of fairly simple tools that basically allow people to do self-serve analytics. It all runs in a browser, because what else would you do today? It's a spreadsheet that'll basically work with a few trillion rows interactively. So it's a Google Docs kind of on steroids, and basically it has a grammar of graphics built in, so you can build all your visuals very quickly. If you know R, then you know the history of that. So basically you can, you can basically download, so in the field you can download it onto an Amazon instance. From an Amazon instance, a really junky one, basically, and you can pull down the product, install it, take a billion records to 60 million records, render it, in sort of 70 milliseconds on a junk machine. So you've got the thing up back in 6 seconds, and that's basically going from Canada to an Amazon machine in the US, because the person's out in the field. Just the implementation technology, just to mention it, basically it's nothing fancy. It's JavaScript and Chrome. A lot of painful JavaScript. Be very scary if you actually have to build stuff with JavaScript. We're really, I would say, pretty strict about how people write JavaScript. We've turned WebStorm up with all the locks on what you can use and so on. We do everything in serialized binary, so we don't have to put up with all the madness of trying to use all URLs encodings and bogus ASCII and so on, because we actually work with time. So time is a native type in our database, so time in nanoseconds is a basic type, and we have sliding window operations. So GUIDs are native types, 64-bit numbers, and none of those go very well in JavaScript. So basically we traffic in tables, all the data conversion, everything's handled on the server, all the rendering's done on the server. We use SVG, so we can bucket and render a million or billion points into a heat map in parallel. If you use D3, it'll just fall over. It'll fall over because there's so much data it'll choke, or because it can't render it because it's too slow trying to feed it to the DOM. We did it all wrong. I wasn't brilliant to doing this. We built everything the wrong way 3 times. So, and we use a few specialized C libs where appropriate. And of course, we use Python, R, and everything else that the customer wants to be able to do. So I think I'm at a point where I should shut up. So hopefully that gives you an idea of the kind of approaches we're doing. We work interactively with 40 or 50 terabytes. So we're not really up there in the big league yet, but that's on a single box. We'll handle trillions of data. We have people that handle most of the stock market and so on 1 or 2 boxes, one being backup. So you don't have to have a really big, ugly, unmaintainable cluster with a falling over zookeeper trying to manage them if you use your brain. And Mark also testified to that. His chosen weapon happens to be Haskell. Ours happens to be a vector functional language. But the parallels in terms of the solution approach, the cost and the performance, are at least 2 very significant data points that tell me that there's another way to do things. I'm not claiming this is the best or anyone should go this, but it works really well. We do the same thing, by the way, in telecom and other markets, but I wanted to talk a bit about finance. And the good news is there are some good guys in the financial market, and we're working very hard to try and make sure that we don't go through the same kinds of things that happened in the past that almost destroyed our economy and the world. And we've got a bunch of committed people, both in the cyber intelligence community and also in the financial community, that are working very hard to try and provide solutions and use the best technology and the best people to, in some small way, make our world a safer and better place. Thank you.